example from the epsilon delta definition, and then we'll start continuity. That was on page 117. Okay, problem 4. We did 3 last time. We want to look at problem 4 now. So let's look at the graph, and I'm going to have to copy it in a minute so we can talk about it. Use the graph, the given graph of f of x, which is x squared, to find a number delta such that. So I'm going to copy this. The function is x squared now. It was the square root of x last time. Oops. And now it's x squared. So we're going to go through the steps, the same steps as before. Ready? To find the delta for the given corresponding. Okay, so this is problem 4. Yes, on page 117. And this is f of x equals x squared. And I'm going to copy this for you so we can talk about it. So this is x squared, just on one side. We don't care for, so this is 1, and this is 1. And they say this is 1.5, and this is 0.5. And of course, we're drawing horizontal lines. And we want to determine the appropriate delta, which we already know it will be this or this, for sure. Will it be this quantity or this quantity? The smallest of the two. Awesome. Great job. Very good. So now, as we know from before, from the precise definition of the limit, we have x minus, or 0 less than x minus, what is a in our problem? 1, very good. Less than delta. This will always imply what is f of x in our problem? F of x. X squared, very good. Minus the limit. The limit is 1, very good. Less than epsilon. However, in the problem, we are given the epsilon. This is not a general abstract proof, but it's a specific. Yes, please.
So it doesn't say like the limit is limit to x or something like in the.
No,
So how would
that
you
is
always
true.
find it? Is it always going to be the number on the x path on the x axis?
Which one are you talking about? Are we talking about A?
The second one. So limit. It's always going to be that one.
Yes. Yes.
And then x is the first one.
Right. So when x is A, this is f of A.
Gotcha.
Good. And what is epsilon in our case?
0.5.
Epsilon is indeed 0.5. Is this distance, which is 0.5, which is epsilon. Very good. So all we have to do, the whole problem reduces to solving this inequality with absolute value. And then, of course, finally getting this. This is my target. We will always start here, and we want to get that, like we do with any precise definition of element. Okay, so how do I convert this? If you remember from last time, negative 0.5 less than x squared minus 1 less than 0.5. This is the translation. You have to remember that, please. So the absolute value of a quantity less than a number means we are trying to find numbers whose distance from 0 is less than 0.5. So in between negative 0.5 and 0.5. Is that clear, everyone? Perfect. So of course I will have to, because I'm trying to build this. I'm done when I build this on this side and some number on the other. And then I say I'm done. So what will I have to do next? Add 1 indeed. So 0.5 less than x squared less than 1.5. Now what I'm going to do is not 100% legitimate unless everything is positive. And everything is positive. This is positive, this is positive, this is positive. This is an inequality, a double inequality if you want. And I'm not allowed to take square roots, but since they all are positive, I am. So then the square root of 0.5 is less than x is less than the square root of 1.5. Now, remember, I am after this. So what should I do to all three sides to have in the middle x minus 1? Right, subtract 1 from all three sides. So then I have the square root of 0.5 minus 1 less than x minus 1 less than the square root of 1.5 minus 1.
Is that one on the last problem that we did? We subtracted 4?
Exactly. Remember, I'm after this. Bless you. I must obtain this in the middle.
Okay.
Okay, and now stop for a second. I want to explain something. If we have the absolute value of x minus 1 less than 3, we will write negative 3 less than x minus 1 less than 3, correct? So now here we have x minus 1 in the middle. And we have two different possibilities. Let's calculate that. Did I bring my calculator? I did. So let's approximate 2 decimal digits. I'm not really interested in. So 0.5 minus 1. So this number here is negative 0.29, and the square root of 1.5 and then minus 1 is this number is 0.22. So there are two options. There are two options. One, I say x minus 1 less than 0.22, and the other one, x minus 1 less than 0.29. Stay with me for a second. So this will mean negative 0.22 less than x minus 1 less than 0.22, and this one will mean negative 0.29 less than x minus 1 less than 0.29. And as we already agreed, we have to choose the smallest of the two. So this one is between negative 0.22 and 0.22. That one is between negative 0.29, I'm exaggerating, for the distance is very tiny between those two, 0.29 and 0.22, right, is 0.07. So I'm either here with 0.22 or I'm here with 0.29. In other words, before you answer, this is 0.22 and this is 0.29.
It's 0.22.
So therefore delta is 0.22. Yes.
So I took the square root of 0.5 and subtracted 1 and got negative the negative 0.29.
Impossible.
Do I subtract?
So the square root of 1.5 minus 1 is 0.22. You didn't put parentheses. You included 1 underneath or something.
Yeah, okay.
Okay, that's impossible. Because the square root of 1.5 is bigger than 1.
Okay.
So the answer cannot be negative. Is that clear? The square root of 1.5 must be bigger than 1. Is that okay?
Yeah, I was talking about the 0.5.
Oh, so this one is not negative 0.29?
Oh no, that's what I got.
Right.
But I guess what I'm asking is, even though it came out negative, you would still bound it from negative 0.29 to.
That's why I gave this example, to help you understanding, and your understanding that x minus 1 less than 3 means between negative 3 and 3.
Okay, that's what.
Yeah,
okay.
that's why I
understand it.
showed this example just to refresh your memory. This is just an example, it has nothing to do with the problem.
Yeah. Okay.
Just to show you that when we say that the distance between x and 1 is less than 3, that's what we mean. X minus 1 can be between negative 3 and 3. Is that better?
Yeah. Yeah.
Okay, so therefore, what do we choose? Final answer?
0.22.
Yes. So delta equals 0.22. Whenever epsilon is 0.5, delta will be 0.22. Any questions for me here?
We would have to write out the.
You don't have to write out anything in this case. You're only asked to find delta.
Okay.
You're only asked to find delta. Very good. So let's move on. Any questions? Anything else for me? Anything else? Okay, so yes, please. Huh?
Is that like the only way to do it?
No, what do you have in mind?
Well, I don't really have anything in mind, but I was just asking, like, I was curious.
No, I guess maybe you can find something else. I wouldn't say that this is the only method, but I don't see any other. Yeah, is there any problem with it or?
No, I just maybe I was thinking maybe there's like one, there's not multiple steps.
No,
Like,
no. Probably the calculator, but no,
okay.
no. Okay, so our next step is 2.5, which is continuity. Continuity. Very important concept, and I'll explain in a minute why. Continuity means a function that is continuous, right? Before we identify continuous functions, there are many continuous functions, let's talk about how a function can be discontinuous. How can it be discontinuous? Yes? Yes, that's one option. We call it a jump. This is a jump discontinuity. That's one. Here's the second type. What do you think this one is called? Exactly. Infinite discontinuity. And there is a third one. Say it again. Yes, very good. Awesome. Great job. Removable. Here's the condition for removable. So assuming that this is A, of course, limit as x approaches A from the left of f of x equals the limit of f of x as x approaches A from the right. Do you agree? The limit from the left equals the limit from the right? But what happens here, it does not equal f of A. This is the condition for a removable discontinuity. The limits left and right are the same, but the function value does not equal the limits. Why is this called removable? Is because this is the only situation in which I could change, define this function slightly differently and make it continuous. Here there is nothing I can do. This will always stay discontinuous. There's nothing I can remove an infinite discontinuity. But this one is called removable because it can be removed. I can create another function that has that is continuous by simply filling this in. The two limits must be the same. As you see here, the two limits are not the same. The two limits are not the same, and even if they were the same, this is still infinite, and it does not exist. Okay. So a theorem here, polynomial functions are always continuous. or are continuous on negative infinity to infinity, everywhere. Polynomial functions are the nicest. And the rest of the functions, like what? Rational, radical, natural log, common log, exponential, trig, all of them are continuous on their domain. They're all continuous on their domain. Polynomial functions are continuous everywhere. Here's a question for you before we look at examples and before we introduce one more definition. The sum, product, difference, ratio of continuous functions are bless you, are. If I add two continuous functions, what do you get? What do you think the result is? What type of function? Of course. If I multiply or divide two continuous functions, the result will be continuous. Of course, on the domain, because especially for the ratio. Okay, so just be careful with the ratio. But any combination of continuous functions is also continuous. Continuity at a point. Continuity at a point. So coming back to the removable discontinuity for a second. How do I make this continuous? The limit from the left and the limit from the right are the same. How do I make it continuous? If those two limits equal the function value at a. So that's the definition of continuity at a point. The limit from the left equals the limit from the right, and it equals the function value at that point. So let's write it. Continuity at a point. Limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right equals f of a. That's the definition of continuity at a point. I will ask you about this definition. Put a big star next to it. I will ask you about this definition. Okay, continuity from the left. Continuity from the left. Here's an example of a function that is continuous from the left. Why? Because the limit of f of x as x approaches a from the left equals the f of a. Can anyone dictate limit continuity from the right? The limit from the right of f of x as x approaches a from the right, in other words, will equal this is continuity from the right. Can anyone dictate the relationship or the equation or whatever you want to call it? Limit as x approaches a from the right of f of x equals? That's it. That's continuity from the right. Any questions for me?
So if it's not filled in, it wouldn't.
It doesn't
It
exist.
doesn't.
The point does not exist. The limit does, but the point does not exist. Very good.
So,
Yes?
so they equal each other.
So if the limit from the right equals the function value, then the function is continuous from the right. If the limit from the left equals the function value, which it does, this function is continuous from the left. Better?
Yeah.
Good. Other questions here? Okay, I want to draw your attention to something that we did in the past, and I said I'm going to come back to it. What did I say about this limit law? What did I say? That we did basically did what?
Brought the limit inside.
We swapped the operators, basically. The limit operator went inside and the square root came outside. And I said that this is extremely important. We're going to use this concept later. It's of swapping of the operators, but I also said it's not allowed in all cases. And it is allowed only under the continuity conditions. But we didn't know that then. So now I would like to show you the theorem. I'm not going to test you on this theorem, but we are going to use it. Not today, however. That's why I don't even want to mention too much or talk about too much about it. But let's read it together. It looks very difficult and sophisticated. It's not. If f is a continuous function at b, and here it is, b, and the limit of g of x as x approaches a is b, right? Then the limit of f of g of x is f of b. Forget about that. Just look at this. These are the conditions, of course. This is the condition of continuity without which this relationship cannot be valid. You saw we used the limit, then we had the square root of a function, and now the square root is outside and the limit is inside. So the limit now touches g of x and f is outside of the limit. So this is allowed only if these conditions are fulfilled, which means conditions of continuity. That is why in this situation, under continuity, oops, I didn't mean that. Under conditions of continuity, we are allowed to swap the operators. The function goes outside and the limit goes inside. So that's a very important theorem, and we'll get to it later. Okay, now I would like us to look at a piecewise defined function, graph it again, and identify where the function is continuous, continuous from the left, continuous from the right. That's the next step. It's up to you. There are 3 problems here, 41, 42, 43. You can choose whatever problem you want. 41, 42, or 43.
43.
43 it is. So let's take a look. So this is problem 43 on 129. We are given f of x, x plus 2, if x is less than 0, e to the x for 0, for x between 0 and 1, and 2 minus x for x greater than 1. So the question is asking us to find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right, from the left, or neither? Sketch the graph of f. We're going to start by sketching the graph of this function. Remember, this is the method I recommend. If you have a better one, disregard mine. I don't want you to switch to my method unless you consider it easier and you understand it. If you have your own that works, don't change to mine. So I prefer starting by writing negative infinity to 0 here because that's what the interval means. And here I have 0, comma 1 with brackets on both ends, and this one in interval notation is 1, comma infinity, because for any function you ask me to graph, I would have to find its domain. That's the starting point. So can you please tell me what is the domain of this function? Yes, because we have everything between negative infinity and 0. We have everything between 0 and 1, including 0, including 1, and everything between 1 and infinity. So the domain must be this. Very good. Then we'll start our table. Which numbers have to be in the table? Because the function changes from one to another type of function at those numbers. And the correct answer is 0 and 1. I will copy the symbols given by the interval notation. Under 0, a left parenthesis and a right bracket, and they're touching. Under 1, I will copy the same thing. 1 to the left with a bracket and 0 with a parenthesis to the right. I didn't do anything. I just copied from the interval notation. Nothing changed. Now, although you're going to say, but this is an overkill, I'll say I agree. But I want to see those functions, those pieces up here. Why? Because this may not be arranged in the correct order from left to right. It may not. If they want to trick us, they may not arrange them in the correct order, and then who knows what we come up with. So the first interval uses which function?
X plus 2.
Of course. The second one, of course, e to the x, and then 2 minus x. This is a linear function. I'm going to choose -2 because -2 gives us the x-intercept. I'm going to plug in 0, although you will say don't. You're not allowed to. I'll say yes, I agree. But I have to, and I put 2 inside the parenthesis. I plug in 0 on the other side, and I get 1. And I know that there is a gap here. The limit from the left of 0 is the limit, perfect. The limit from the right of 0 is 1. So obviously the limit from either side of 0 will not exist. I'm here now with 1, so this is e. I'm here now with 1, and this is 1. And with 2, and I get 0 for the x-intercept. What is the limit from the left of 1? What is the limit from the right of 1? So obviously the limit from either side of 1 does not exist. The numbers are different. So obviously I already found the discontinuity here and here. So let's graph the function.
I have a question.
Please stop me if you have anything.
For the 2,
Yes,
all the way to the left on the f of x, why can't we include that?
I'm not allowed to plug in 0 in this branch. 0 is not here. 0 is here.
Oh, 0. Okay, 0.
That's why it's a parenthesis.
Right.
That's why it tells me that this will be an open point and the bracket will be a full point. That's why I'm using these symbols.
Okay.
This will mean an open point, this will mean a full point.
Okay.
Better?
Yep.
Perfect. So -2, 0. 0, 2, but that will be an open point. And this is the first branch. And we can't change that. We cannot extend it to the right. Please be very careful. Now, 0, 1, this is a full point. And 1, e is roughly 3. So this is 0, 0, 1, 2, roughly 3, and this is a full point. And if you remember the graph, let's graph e to the x, please. We can never forget e to the x. It doesn't touch here. I'm sorry, for some reason I'm too close. So this is the graph of e to the x, and that's a little piece of it. And now the last portion, 1, 1, and this is a open point, and 2, 0, and this is a full point. So this is the graph of the function we had f of x. I will ask you, can anyone give us the range of this function? And before you say anything, the range is determined by, just imagine that you cut the function with horizontal lines. If it hits the graph, it's okay. If it doesn't, you have to stop. It hits the graph, yes. It hits the graph, yes, 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 yes. No, 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 no. Negative infinity to e. Awesome. Well done. So where is this function discontinuous? Discontinuous at x equals 0 and x equals 1. At 0, is the function continuous from the right or from the left? Or none of the above? Is the function at 0 continuous from the left, from the right, or none of the above?
To the right.
Indeed, of course. The limit from the right equals the function value. Continuous from the right. What about at 1? Continuous from the right, from the left, or none of the above? Very good. Very good. Okay. Before we look at the intermediate value theorem, I would like us to look at one more problem. Questions, please, for me. Anything? Yes, please, Greg.
Can you
Yes?
explain the continuous from the right and then what you wrote underneath it again?
Oh, I just didn't want, I was lazy. I didn't want to copy all this, and I just wrote.
Is that
Yeah.
saying that x equals 0?
At x equals 0, the function is continuous from the right.
Okay.
Here's why. The limit from the right of 0, the limit from the right at 0 equals the function value at 0.
Okay.
And here at x equals 1 is continuous from the left because the function values as x approaches 0, x approaches 1 from the left equal the function value at 1.
So what's discontinuous then?
The function is discontinuous, not continuous at 0. The
At
definition.
at the actual.
The definition of continuity is the limit from the left equals the limit from the right equals the function value.
Right.
But at this point, the limit from the left does not even equal the limit from the right. So these two are not the same.
Oh, okay. I'm coming from the left and right. It's continuous. But
Yes.
At the actual point.
Yes.
Discontinuous.
Yes. At that point is discontinuous. It's a jump discontinuity in both cases. This is a jump discontinuity at 0, this jump discontinuity at 1. So I'm going to say jump. Jump discontinuity at x equals 0 and at x equals 1. A continuous function requires that when I graph it, I never lift the pencil off the paper. If I have to lift and jump up here, that's not continuous. Very good. I would like to look at a problem like 45. Let's read it together. These are the problems recommended in some of them are the ones recommended in the list of the recommended problems. For what value of the constant c is the function f continuous everywhere? So I'm going to copy the function. We're going to find the parameter c, so that this is always continuous everywhere. So let's do that. So this is problem 45, 129, and here's the function. F of x equals cx squared plus 2x for x less than 2, and x cubed minus cx for x greater than or equal to 2. In such a problem, I have to write, first thing, cx squared plus 2x and x cubed minus cx are functions as, functions. So these two functions are always continuous functions as, what type of functions are they? Exactly. Exactly. So this is extremely important. Are always continuous functions as polynomial. They're always continuous, as we discussed a few minutes ago. Number 2, continuity at x equals at x equals
2.
exactly. What has to happen for this function to be continuous at 2?
The left and right.
Exactly. The limit from which expression as x approaches 2 from the left equals the limit of which expression for as x approaches 2 from the right, and equals f of 2. Can anyone give us the left portion?
Cx squared plus 2x.
Very good. Can anyone, I know it's redundant, I know it's silly, but I'm waiting for you to give me the second one. Very good. No, I'm not testing whether you're awake or not. So can anyone give us this result, and anyone else can give us this result? Please? How much? Say it again. Very good. 4c plus 4 must equal yes, 8 minus 2c must equal f of 2. Which branch will you use for f of 2? You can only use one. Very good. So 2 minus 2c, 8 minus 2c. So this is redundant. I don't need this portion. But from here, what will I have to determine? Exactly. Very good. So
you would, what happened to the top, or how it equals f2? Did you just plug in
it's the
2?
same thing.
Oh, okay.
That's
just
why
plugs
I
in.
don't need to use twice.
Gotcha.
So then 4c plus 4 must equal 8 minus 2c. I move c, I move forward, so I get 6c equals 4, or c equals 2/3. I go back and plug it in, the function. So I have 2/3 x squared plus 2x for x less than 2, and x cubed minus 2/3 x for x greater than or equal to 2. Is guaranteed to be on everywhere. We made it continuous. Now, if you want to change c from 2/3 into something else, the function will not be continuous. We forced continuity at that point by setting the limit from the left equal to the limit from the right, and to the function value at that point. We solved the equation, we got 2/3. Now it's guaranteed, if you want to determine the limit from the left, it will definitely equal the limit from the right, and the function value at that point. So we determined the parameter c such that the function is continuous everywhere. Any questions? Any questions? Last theorem here in this section, or you can move on. Intermediate value theorem. Intermediate value theorem. Here's a question for you. Let's assume I have a function, this function, f of x, and I have here a and I have here b. Do you think that f of x equals 0 has solutions or not?
Yes.
Right here, of course. I'm going to call that C. C is the x-intercept or the 0 of f of x. Okay, so what am I saying to you with this? Here's what I'm saying to you. If f of x is a continuous function on the interval a comma b, is it a continuous function on the interval a comma b?
Yes.
Perfect. And f of a is less than 0, and f of b is greater than 0, I'll put in parentheses, or vice versa, meaning f of a is positive and f of b is negative. In other words, we say it changes sign. There must be a c in the open interval a comma b such that what?
C equals 0.
Of course, this is the intermediate value theorem. It's a version of it. It's the one that I personally care for. F of c is 0. No question about it. Notice one thing. The intermediate value theorem does not give us a solution, does not find the solution. It only says it has one, and it's between a and b. But that a and b should be 1 to 2, or 2 to 3, not -5 to 10. That's not an interval. We want an interval of 1 unit length or smaller, not bigger than that. So why is this theorem so important? It's very important because in chapter 4, we will be using it to determine and solve any equation that you can think of. We have a tool, but we have to wait till chapter 4, in which we will be able to solve any equation that we are not able to. So, like for example, here's one, 56. Natural log x equals 3 minus 2x. 56, and this is 129. Natural log x equals 3 minus 2x. Who can solve this equation? Not by hand. Not by hand, no. Okay, so let's do this. With a graphing calculator, please. You can use mine if you don't have one. I have an extra here. Let's go to y equals. Clear if you have anything else in there. And before I do this, I'm sorry, we need to create the function. So solving this equation or solving this equation is the same thing. And this is our function f of x. Would you agree that solving this is the same with solving this? Yes? Okay. So this is the function that I need to put in the graphing calculator. So we have natural log x don't forget parentheses, minus 3 plus 2x. Okay? And then I go to second and table. Let me check, I think, yeah, this goes to default all the time. So make sure that, go to second and table set and make sure that the independent variable, just the independent variable, is in the ask mode. And after that, go to second and table. And I'm going to plug in some numbers. I know the natural log is let's also graph natural log. So let me refresh your memory on the graph of natural log. Natural log is not defined on everything. It's defined to the right-hand side of 0 only. So what am I trying to do with the graphing calculator? I'm trying to find an interval in which the function is negative and then positive, or positive and then negative. But I can't start with negative numbers because I can plug in natural log negative numbers. Okay, so let's say I'm going to plug in 0.1 because I can't plug in 0. Then it's negative. Then I'm going to plug in 1. It's negative. Then I'm going to plug in 2. I got it. I got an interval in which the function changes sign from negative to positive. So I will say this. F of x is a continuous function on the interval 0 to infinity, because this is continuous everywhere, but this does not exist to the left of 0. And f of 1 is negative. I don't even care for the number. And f of 2 is positive. Therefore, by IVT, intermediate value theorem, there exists what? C in the interval 1, 2 such that
What is next to the C?
Therefore, by IVT, the intermediate value theorem, there exists C in the interval 1, 2. That's our interval that we picked.
F of C is 0.
Of course. So one more time, as you notice, the intermediate value theorem only tells us you're looking for a solution. Well, it's here between 1 and 2. How much? It doesn't provide that. What is it? It does not know. But it only indicates you will find a solution guaranteed if the function is continuous. If the two hypotheses, if the function is continuous and it changes sign, either from negative to positive or from positive to negative, there must be a solution between those two endpoints of the interval. Is this clear? Does it make sense? Yes? Okay, that's the intermediate value theorem. Do you think we need another example, or we move on to limits at infinity? Yes. Okay, so let's say 55. On the same page, 129. Cosine x equals x cubed.